Hello, this is Lucia with the Nevada Division of Minerals, and thank you for tuning in to listen to this talk titled, All That Glitters is Not Just Gold, Critical Minerals in Nevada. This is the general presentation outline. We will review the definition of critical minerals in Nevada, critical minerals on the global scale, and critical mineral activity in Nevada. We will conclude with a quick review of some online data resources. What is the definition of a critical mineral? A critical mineral is a mineral that has been 1. Identified to be a non-fuel mineral or mineral material essential to the economic and national security of the United States. 2. From a supply chain that is vulnerable to disruption. And 3. That serves an essential function in the manufacturing of a product, the absence of which would have substantial consequences for the U.S. economy or national security. On May of 2018, the final list of critical minerals was published in the Federal Register. Of the 35 critical minerals listed, Nevada contains known occurrences or deposits of 21 of the 35 minerals. Occurrences are bold, and past production is signified with an asterisk. Critical minerals occur in more than 60% of Nevada's historic mining districts, some more commonly than others, and several historic mining districts have more than one documented mineral occurrence or deposit. Minerals that are lucky enough to land themselves on the list of critical minerals must each be scrutinized independently of one another. There are many questions that need to be addressed, such as, what is the economic vulnerability of the individual mineral? How geographically concentrated is the source of each mineral? What is the disruption potential? What is the foreign ownership of the mineral assets and operations, including processing facilities, and so forth? Each commodity and form of that commodity utilized must be evaluated in detail, and where supply chains are convoluted, this may be a difficult task. Also, without a functioning crystal ball, it is hard to see what technologies may emerge in the future which could impact supply and demand. Hence the reason for an ever-evolving list of critical minerals. I would like to touch on data sources right now instead of at the end. Starting with the next slide, we will be viewing a series of maps which show some pertinent information for each of the critical minerals that have known occurrences or deposits here in Nevada. The data for the following series of maps were obtained from the USGS and the Fraser Institute's annual survey of mining companies. While some of the USGS data is dated, these data sets are the only global representations of commodities such as arsenic, bismuth, fluorspar, magnesium, potash, and tungsten, which were not addressed in the 2017 USGS report on critical mineral resources of the U.S. Therefore, they were not included in the 2017 Critical Global Minerals data set, which is also included in the maps we will see shortly. In all maps, excluding the 6 commodities listed previously, all 4 layers shown here in yellow have been utilized. Keep the vintage of the data in mind if something you know exists is missing. The USGS is currently working on updating these data sets and anticipates a big data publishing year in 2022. The maps we will be seeing will all look similar to this. The glowing dots on each map represent U.S. mines and plants, mineral operations outside the U.S., major mineral deposits of the world, and global critical mineral deposits, mines, districts, and mineral regions. Countries, states, and provinces are color-coded according to their investment attractiveness ranking in the 2020 Fraser Institute's annual survey of mining companies, red being the highest ranking jurisdictions and yellow being the lowest. Those regions lacking color either did not respond or did not provide enough data to be evaluated in the survey. The countries that are import sources for the U.S. for the highlighted commodity are outlined in white. Each slide supplies a list of commodity forms considered critical, a summary of domestic mining and secondary production from 2018 to 2019, global production during the last 10 to 15 years, import sources from 2016 to 2019, alternative supply options, major uses as presented by the USGS in their 2017 and 2020 publications. Also shown in the bottom right-hand corner of each slide is the 5-year average of our net import reliance calculated from figures presented in the USGS Mineral Commodity Summaries 2021. Import reliance refers to the reliance on foreign sources for raw and processed mineral materials. Rolling in alphabetical order, we will start with antimony. Antimony is used to manufacture several items, including lead acid batteries, like the ones found in many vehicles, backup power facilities for cell phone towers, hospitals, and standalone power systems, ammunition, lead alloys, ceramics, glass, and rubber products. It is also used as a flame retardant in items like mattresses, workwear, and textiles. Some mining has taken place in the last 10 years here in the U.S., but no mining was reported in 2020. There is one metal producer here in the U.S. who is totally reliant on imported feedstock. The U.S. 5-year average net import reliance for antimony is 83%. We import from several regions of the world, which are listed in the screen. China is the leading global producer of antimony, followed by Russia. Some alternative supply options for antimony include recycling and further research on deposit models to further assist in exploration. Arsenic. Arsenic is mainly used as a wood preservative and for the production of pesticides, herbicides, and insecticides. As a metal, arsenic is used to make alloys and semiconductors. Semiconductors control the flow of current in electronic devices and equipment and are used in integrated circuits, telecommunications, solar cells, and special optical materials. Recovery of arsenic in the U.S. is generally not economical, so it is disregarded, resulting in a 100% import reliance. China, Japan, Morocco, and Belgium are the main import sources for the U.S. There is very limited recycling of scrap. Some supply options include more recycling of scrap, recovery of arsenic from smelter residues, and the development of new processing methods which would make domestic extraction economical. Barite. One of the main applications of barite is as a weighing agent and filler in drilling fluids, which are used in mineral exploration, oil and gas, and geothermal borehole or well drilling. Barite is also used to manufacture rubber, plastics, paints, and glass. Barite production fluctuates globally, mainly due to fluctuations in the oil and gas industry. There is limited domestic production of barite, which only meets a small fraction of total U.S. demand. Net import reliance is 85%. Substitution, deposit model research, and new processing methods are options put forth to reduce foreign reliance. Beryllium. Beryllium is crucial for defense applications such as radar, telecommunications satellites, infrared target acquisition systems, surveillance systems, and electronic countermeasures systems. It is also used as an alloy for underwater pressure vessels, telecommunications, electronic connectors, shielding, and aircraft landing gear. The U.S. is the leading producer of beryllium, but production of this crucial commodity is from a single mining company in Utah. Net import reliance is calculated by taking imports minus exports plus adjustments for government and industry stock changes, which, in the case of beryllium, leaves the U.S. 13% net import reliant. Minor domestic recycling is taking place. During the last 10 to 15 years, U.S. production has remained consistent, where Chinese production has doubled. Options for securing beryllium supplies include developing assessment models for new deposits and more efficient extraction methodologies. On to bismuth. Owing to its antimicrobial properties, bismuth is largely used in the pharmaceutical industry to treat stomach ulcers, burns, intestinal disorders, and acid reflux. Bismuth is also used as a lead substitute in plumbing applications, and in smaller amounts, it is used to make ceramic glazes, crystalware, semiconductors, and triggering mechanisms for fire sprinklers. Bismuth is contained in lead ores mined domestically. These ores are shipped and processed outside of the U.S. Recycling accounts for less than 10% of U.S. consumption. Global production during the last 10 to 15 years has remained consistent, with over 1/2 of the world's processed bismuth coming from China. The average net import reliance for bismuth comes to 96%. The U.S. relies on China, Korea, Mexico, and Belgium for imports. More recycling and increasing the recovery rates from lead ores could help to maintain domestic bismuth supplies. Cobalt. Cobalt is used to make batteries for our electronic devices and electric vehicles. It is also used to make superalloys, which are then utilized in magnets, steels, chemicals, and gas turbines, like those which generate power from geothermal plants, nuclear power plants, wind farms, and natural gas plants. One active mine in Michigan and mine tailings from Missouri produced cobalt-bearing concentrates. These concentrates were exported internationally for processing elsewhere. Recycling of scrap significantly contributes to U.S. supplies, lowering the average net import reliance to 73%. The Democratic Republic of Congo is the largest global source of cobalt, though China dominates refinery production. Imports of cobalt to the U.S. are sourced from the Democratic Republic of Congo, Norway, Japan, Finland, and China. Supply options include recycling, better geologic models to assist in the exploration for new deposits, and new methods which would increase recovery and processing. Next up, fluorspar. Fluorspar is used to produce many common materials that we use every day, like aluminum, steel, glass, and cement. Fluorspar is also used to manufacture chemicals such as fluorocarbons and fluoropolymers. Fluorocarbons are used in cooling systems, heat pumps, and fire suppression. Fluoropolymers are utilized in the manufacturing of laptops, cell phones, satellites, fiber optics, lightweight vehicles, and much more. Metallurgical grade fluorspar is mined domestically in limited quantities, but there is no mining for acid grade fluorspar, and there is also no recycling. The U.S. is 100% reliant on fluorspar imports, most of which come from Mexico. Vietnam, China, and South Africa are secondary import sources. Global production of fluorspar has remained stable, with China producing over 50% of the global supply. Domestic supply options include possible extraction from brines and emphasis on discovering new conformable fluorspar deposits. Gallium. Gallium is crucial to the functionality of many electronic applications, like the computer or electronic device that you are using to view this video, along with cell phones, microwave circuits, infrared circuits, light-emitting diodes or LEDs, and diode lasers. There is no domestic mining of gallium, though we do refine imported crude gallium, making the U.S. 100% reliant on imports. China leads the globe in crude gallium production and is the main source of U.S. imports. Secondary sources include Canada, Japan, and Germany. Options to meet consumptive demands include research to understand future impacts on supply, the development of improved assessment models, new and more efficient extraction and recycling technologies, along with more domestic refining and recycling. Graphite. The use of graphite has become more and more important as it is employed to manufacture essential parts in energy technologies such as fuel cells, battery anodes, pebble bed nuclear reactors, and solar cells. Electrodes, refractories, and foundries are also major graphite consumers. While there has been no recent mining of graphite in the U.S., there are some resources currently in development. There is domestic recycling of refractory graphite. The U.S. is 100% reliant on imports. China mines 75% of the world's natural graphite and has some of the largest world resources. China, Mexico, Canada, and India are all import sources for natural graphite to the U.S. Options to aid in domestic supply include exploration, further research into the occurrence and distribution of high-grade flake graphite deposits, and more recycling of refractory graphite. Lithium. Lithium has high electrochemical potential, meaning its ability to store chemical energy, which can be converted to electricity, is high, and this is why it is used to make rechargeable batteries. Lithium is also used in ceramics and glass to raise the melting temperature and in lubricating greases. Here in the U.S., there is one producing mine and two producers of lithium compounds, along with domestic recycling of lithium-ion batteries. The U.S. is greater than 50% net import reliant, and what is imported comes from Argentina, Chile, Russia, and Asia. Manufacturing of key lithium compounds used in lithium-ion batteries is concentrated outside the U.S., mostly in China. Supply options include further research on deposit models, recycling, and the establishment of the domestic lithium-ion battery supply chain. Magnesium. Magnesium is used in the casting of metal parts, like those found in your vehicle. Magnesium is also used as a fertilizer, for nutritional supplements both for animals and humans, for wastewater treatment, and in flooring tiles. Domestic production and recycling of magnesium accounts for a large portion of domestic consumption, bringing the U.S. average net import reliance to less than 40%. Imported magnesium metals come from Canada, Israel, Mexico, South Africa, and Gabon. In order to maintain or improve domestic supply, actions include expanding domestic resources, improving processing methods, and recycling. Now for manganese. Manganese is mainly used in the manufacturing of steel, but it is also used in some rechargeable lithium-ion batteries, alkaline batteries, and non-rechargeable lithium manganese dioxide batteries. In aerospace and other transportation applications, electrolytic manganese metal is used to make non-ferrous alloys. Imported manganese ore is processed domestically. The U.S. net import reliance figure for manganese is 100%. Electrolytic manganese is only supplied by China and South Africa. Manganese ore is imported from several countries, which are all listed on the screen. Options for boosting domestic supply include increasing processing and mining efficiencies, along with discovery of local higher grade deposits. The platinum group metals. One major use of the platinum group metals is in catalytic converters to reduce automotive emissions. They are also used in electronics, dentistry, jewelry, petroleum refining, for the manufacturing of medical grade silicones and antibiotics, for investment purposes, and much more. Platinum and palladium are mined, recovered, and recycled here in the U.S. Other PGMs that are mined in the U.S. are sent elsewhere for recovery. The net import reliance for palladium and platinum is 56%. South Africa dominates global production and is an important source for platinum group metals to the U.S. along with Russia, Zimbabwe, Canada, Germany, Italy, Switzerland, and the United Kingdom. Supply options for the U.S. to meet increasing demand include further developing the recycling process for the recovery of other platinum group metals and further research into platinum group metal formation in other geologic settings. Potash. Potash is widely used in agriculture as a fertilizer due to its soluble potassium content. It is used as nutritional supplements for livestock, general purpose food additives, water softener, de-icer, and flux in glass manufacturing. Potash is also employed in aluminum recycling, explosive manufacturing, and pharmaceuticals. Potash is mined domestically, but production, which has been decreasing, only meets a small fraction of what is needed. There is no domestic secondary production. The average net import reliance during the last 5 years for potash is 90%. Potash imports have remained consistent for the last 10 to 15 years, with most imported potash coming from Canada. Efforts to increase supply options include defining more domestic and foreign resources. The rare earth elements. A caveat. This summary is very general, and as indicated in the beginning of this presentation, each of the 15 elements which make up the rare earth element category should be analyzed individually rather than as a group. There are several applications of the rare earths, including glass manufacturing, catalytic converters or emission control on vehicles, oil refining, battery anodes, steel making, computer and cell phone display screen lighting, lasers, nuclear control rods which control the rate of fission, synthetic gems, fertilizers, and magnets such as those used in computer hard disk drives, wind turbines, speakers or headphones, MRI scanners, fishing reels, magnet motors and cordless tools, and much more. Domestic production comes from the Mountain Pass mine, but all ores are exported for processing. Other rare earth element projects are undergoing development. Limited recycling of batteries, permanent magnets, and fluorescent lamps is a minor domestic source for rare earth elements. The U.S. is 100% reliant on imports. China dominates the processing of rare earth elements globally, and rare earth element compounds and metals are imported to the U.S. from China, Estonia, Japan, and Malaysia. Options to boost domestic supply and decrease foreign reliance include diversifying production, reducing waste, developing substitutes, increasing recycling, develop economic extraction methods, and continued research to enhance deposit models. Rhenium. Rhenium is used in aerospace as a plating on aircraft to increase wear resistance. It is used to make superalloys, which are then employed in industrial gas turbines and jet aircraft engines to manufacture the turbine blades. Rhenium is also used as an industrial catalyst in the production of gasoline and to make electrical components, crucibles, electron tubes and targets, as well as thermocouples. Minor amounts of rhenium are produced from the roasting of molybdenum concentrates here in the U.S. The U.S. is a leading producer of secondary rhenium. The U.S. net import reliance sits at 81%. Chile supplies most of the U.S. rhenium metal powder, where Kazakhstan supplies the majority of ammonium perrhenate. The market for rhenium is still small. Demand is mainly for the production of turbines. Research on rhenium contents in ore deposits and the general geochemistry of rhenium deposits are focal points in attempting to increase or maintain supply. Tellurium. Tellurium is used to manufacture solar photovoltaic cells which convert light energy into electricity. Tellurium is also used as additives to copper and lead alloys, in thermoelectric devices, in cast iron, and in the production of rubber. Some tellurium metal is mined with copper here in the U.S. and is recovered during refining. There is very limited recycling in the U.S., leaving the average net import reliance greater than 95%. Most tellurium is imported from Canada, China, Germany, and the Philippines. According to the USGS, the near future recovery of low copper grades may force recovery of oxidized copper ores by solvent extraction. In this process, it is not possible to recover the tellurium as a byproduct, as is possible through the smelting of higher grade copper sulfide concentrates. This change in methodology could potentially lead to greater emphasis on precious metal deposits to meet global and domestic tellurium demands. And future research may focus on methods to recover tellurium from two new sources, one being the extraction of tellurium from iron manganese crusts on the ocean floor, and the second being the reprocessing of old waste piles. Titanium. Titanium is used as a pigment in paints, as a catalyst, in ceramics, in textiles, and due to its strength and corrosion resistance, it is used in aerospace as well as in steel production. All forms of titanium deemed critical are produced domestically, and titanium scrap is imported for secondary production of titanium and titanium dioxide. Though the U.S. is a net exporter of titanium dioxide and metal ingot, the 5-year average net import reliance for mineral concentrates is 91%. Sources for titanium come from several regions listed on the screen. Options to maintain or increase domestic titanium supplies include the development of cost-effective extraction methods from various materials and update the current ore deposit model. Tungsten. Tungsten is used to make alloys or superalloys, which are then used in a variety of applications including aerospace, jet engines, satellites, helicopter rotor blades, and land-based turbines. Owing to its durability, tungsten carbide is used to manufacture munitions, wear-resistant tools, and oil and gas drilling equipment. Tungsten is used to make lighting and specialty filaments, which must have the ability to withstand high temperatures. Domestic commercial production of tungsten has not taken place since 2015. There is some recycling and significant processing of imported ores and concentrates. Our net import reliance sits at less than 50%. China leads global production for all forms of tungsten and is who we source much of our tungsten from. Increasing domestic recycling would assist in maintaining supply. The last critical mineral we will discuss is vanadium. Vanadium is used to make alloys, which are then employed to make things like power-generating turbines and blades for jet engines. It is also used to manufacture batteries for large-scale electrical storage, to manufacture rubber, for petroleum cracking, and in the manufacturing of sulfuric acid, which in turn is used to produce a large variety of items we use every day, such as fertilizers, detergents, paints and pigments, plastics, fibers, rayon, paper, batteries, explosives, and pesticides. There has been sporadic domestic mining of vanadium and some recycling. The 5-year net import reliance average is 98%. China is responsible for over half of the world's mined vanadium. Austria has been the most important source for ferrovanadium and Brazil for vanadium pentoxide. Options for maintaining supply include the optimization of extraction methods and increased recycling. In an attempt to see where Nevada stood as far as importance in all of this critical mineral buzz, we took the 10 highest ranked jurisdictions as far as investment attractiveness, and within each tallied up the mines, deposits, and plants for each of the critical minerals we just discussed. Again, only using the USGS data outlined in the 7th slide. If we look at the count for the number of critical minerals that occur in each jurisdiction per acre normalized, Nevada comes in first, followed by Idaho and Arizona. If we look at the number of critical mineral deposits, mines, and plants per acre normalized that occur within these jurisdictions, Finland comes in first, followed by Nevada, then Arizona. Finland jumps into first place here because there are 29 platinum group metal deposits documented within this region. Bottom line, Nevada appears to be a pretty good place to be exploring for critical minerals. So with that, let's bring our focus back to Nevada and review a little bit about current critical mineral activity in the state, work involving critical minerals from government and state agencies, and conclude with some data resources. Since 1981, there have been no fewer than 323 notices filed with the BLM, with the commodity of interest being one of the critical minerals identified in the 2018 Federal Register list. Keep in mind, the commodity of interest isn't always specified, so no fewer seems like a pretty accurate statement. Currently, there are 27 of these notices whose disposition is authorized or pending. The claimants and/or operators of these authorized notices are listed in the table shown on the right. Since 1981, there have been no fewer than 41 mine or exploration plans filed with the BLM, with the commodity of interest being one of the critical minerals from the 2018 Federal Register list. Again, the commodity of interest is not always or has not always been disclosed. Currently, there are 23 of these plans whose disposition is authorized or pending. The claimants and/or operators of these authorized notices are listed in the table shown on the right. And, for what it's worth, 23,377 mining claims have been staked in mining districts with critical mineral occurrences or deposits since December of 2017. At the state and federal government level, there are 2 large projects in progress that pertain to critical minerals. The first is the Geoscience Data Acquisition of Western Nevada Project, or GEODAN. Several agencies, both federal and state, are participating in this project that focuses on conducting airborne geophysical and 3DEP, or three-dimensional elevation program, LiDAR surveys over Nevada and California in an effort to collect information on undiscovered geothermal, critical mineral, and groundwater resources in the Western Great Basin and the Walker Lane region. There has been a $10 million investment in Nevada to meet the project goals, which has many benefits as highlighted on the screen. The Nevada Bureau of Mines and Geology is actively involved in this project. The second project involving critical minerals at the state and federal government level is the Earth Mapping Resources Initiative, or Earth MRI. The goal of this project is to improve knowledge of the geologic framework to identify areas with potential to contain undiscovered critical mineral resources and to decrease the nation's reliance on foreign resources of minerals critical to our security and economy. This project consists of a partnership between USGS, state, and other federal agencies. There are 2 ongoing projects and 2 documented future projects that the Nevada Bureau of Mines and Geology will be participating in. The 2 ongoing projects are the Mountain Pass and Clayton Valley or Rhyolite Ridge projects. The 2 future projects will be in the Humboldt Complex and in the McDermott area. Moving on to data resources. First stop, Mr. Data, the USGS Mineral Resource Online Spatial Data Site. This is the source for most of the geospatial data shown in this presentation. There is a variety of great geospatial data that is possibly dated but free to use here. Types of data include mineral resource, geological, geochemical, geophysical, and geochronological data, all of which are downloadable. Here at the Division of Minerals, we have put together some web maps that focus on critical minerals. To access the content, scroll down to the Pages Listing section on the homepage of our Open Data site and click on the Nevada Mineral Producers, Commodities, and Occurrences page. If you scroll down towards the bottom of the page, you will come to the Critical Minerals section, where you will find a video tutorial for the web applications we're about to review, 2 interactive web maps, and a couple PDF maps, including the colorful mining districts map shown earlier in this presentation. This is the first web map you will come to. This map contains historic mining claim listings, notices, and plans, along with Tingley's historic mining district data, which has been filtered to display those mining districts with critical mineral occurrences or deposits. And of course, all maps are interactive and have pop-ups, which will give more information on the features presented within. If you scroll down on the page, you will come to another web map, which will compare current and historic data with respect to mining districts known to contain deposits or occurrences of critical minerals. When we zoom in on this particular map, current mining claim point listings, mining claims per section, major mines, and authorized or pending notices and plans render in the map panel to the left. In the right-hand map panel, historic mining claim point listings and any notices that are closed, canceled, or expired are displayed. Map extents will always mirror one another. The legend can be displayed by clicking the double arrows outlined in blue in the upper right-hand corner of the map panels. The information box can be minimized by clicking the double arrow to the right of the box, which is outlined in red. We will click on some points within the map, and you can see our familiar pop-ups appear. Unfortunately, viewing mass amounts of data in this application is a bit cumbersome, as one cannot view the data in an attribute table. For the option to view attribute tables and for more general functionality, the map we previously discussed is recommended. But this comparative map is great for looking at a lot of data on one screen. The pop-up can be toggled into a list view by clicking on the number of records selected in the bottom right-hand corner of the pop-up, which is outlined in blue. And finally, don't forget about the Nevada Mineral Explorer, which is a web application developed by the Nevada Bureau of Mines and Geology and the Nevada Division of Minerals as a tool for explorationists to identify and discover mineral resources throughout Nevada. This application was created to be a one-stop shop for explorers to view and interact with data relevant to Nevada geology, mining, precious metals, industrial minerals, geothermal resources, along with oil and gas. Data has been gathered from various sources, including the Nevada Division of Minerals, the Bureau of Mines and Geology, the USGS, the BLM, and the Forest Service. And we have come to the end of this presentation on critical minerals. I would like to thank you for tuning in, and I hope that you have a great day.